Hello everyone. My name is Bhusan Chettri, and the title of my talk, it's deep generative variational autoencoding for replace spoof detection in automatic speaker verification. So this is a recent work that we published in CSL journal, and it's a joint work with Tommy Kinnunen and Emmanuel Benitez. So to begin with, let me give you a brief background on automatic speaker verification, spoofing detection, and countermeasures for spoofing detection. So the main goal of an automatic speaker verification system is to verify the claimed identity of a speaker. So is the speaker who he claims to be? So what the system does is it basically
Hello, can you hear me?
Hello. Yes.
Can you please switch off the video because you are breaking down a bit?
Okay, let me quickly. Okay.
And if you can keep your mic next to your mouth, I think is a bit better. Thank you.
Okay. All right. Okay, so am I audible now, Ricardo? Is it clear or?
You're still a bit breaking up.
Hello, can you hear me now?
Sorry, did you use? Are you using the headphones?
Yes.
Can you try to use the mic of the computer? Maybe it's a bit better.
Okay, maybe I'll. Okay, is it better now?
No.
Is it better now?
Okay. Yep.
Okay. So as I said, the speaker verification system basically aims at verifying the identity of speaker. So given to speech utterance, the system basically compares whether the speech utterance belongs to the same speaker or not. So if that's the case, the system grants access to the system. Otherwise, it simply rejects. Common application includes user authentication, for example, in banking, call centers, smartphones, etc. So spoofing attacks basically aims at attempting to gain unauthorized access to the voice biometric system of a registered user. So by voice biometric, I basically mean speaker verification system here. And this kind of attacks can be implemented in 4 different ways. So using synthetic speech generated through text-to-speech technology, or voice conversion, mimicry, impersonation, and replay attack. So replay attack basically is implemented by simply using pre-recorded speech of a registered user to the system. And countermeasures are built to protect ASP system from such attacks. And as you can see, countermeasure is essentially a binary classifier that aims at detecting whether the speech is a bona fide speech or a spoofed speech. So in this work, we basically focused on replay spoofing attack for 2 main reasons. First, because of its simplicity. The attacker doesn't require any expertise in machine learning or speech technology. All that he would require is simply high-end devices. And also, this kind of attack is a bit difficult to detect reliably, because here we are dealing with the actual speech. We are not using any computer algorithms to generate speech, but we are using the pre-recorded speech of a genuine speaker. So this figure actually depicts the difference between a genuine speech and a replayed speech. As you can see, an attacker, let's say, is successful in acquiring a genuine speaker voice speech. All that the attacker would require to do is to play back that recorded speech through some playback device, which gets recorded through the recording device of an ASP system. And all this act happens in some acoustic environment EDAS. So as you can see here, the factors that we are actually interested in distinguishing between a replayed speech and a bona fide speech is basically the environmental factors like acoustic environment impact from the devices, and so on. So the main objective of this work is to perform an initial feasibility study of using variational autoencoders for spoofing detection from two main perspectives. So the first one, we explore VA as a backend classifier. And the main reason for this is because of the popularity of GMM backend classifier in spoofing detection, which is also a generative model. And also we know that variational autoencoders are widely used in other domains, for example, computer vision. And so we wanted to actually perform this initial study on spoofing detection, as VAs hasn't been explored much in this domain. And the second category we explore is use of VA as a feature extractor. So this particular figure A and B depicts our actual objectives. So in the first case, we look at the backend. So we switch between GMM, the traditional backend classifier, and VA model. So in the second category, we use VA as a feature extractor, wherein we take the absolute difference between the reconstructed input and the original input and take this as a new feature representation and train our discriminative classifier on top of it in a binary setting to detect between bona fide and spoofed speech. So in terms of backend classifier, we investigate VAs from multiple perspectives. So we start with the naive VA or the traditional VA, wherein we train two separate VA models to model bona fide speech data and the spoofed speech data. So as you can see, as we all know, VA comprises encoder and decoder. So encoder basically learns the distribution of this latent space, which decoder uses to reconstruct the original input. And the second category of VA we explore is using conditional input. So where we provide the class labels as additional condition on the encoder and the decoder. So everything remains same as we saw in the previous case. So here we have these additional labels. And in this setting, we just train a single VA model, but using the whole training data, both bona fide and spoof, but with obviously constraint on the labels. And the third category of VA we explore is we augment this conditional VA model by a discriminative classifier. So in this, we explore two different settings. The first one, we use this classifier on top of the latent space. So we use this mean latent vector as input to this classifier, and we train this for spoofing detection in a binary classifier. And the second one we explore is we augment this classifier to the output of the reconstructed input. So the experimental setup, we used two publicly available spoofing datasets, ASB Spoof 2017 version 2.0 and ASB Spoof 2019 PA. And in terms of evaluation, we used two traditional metrics. The first one is equal error rate, which basically is a response to a decision threshold where the false acceptance and false rejection rates are equal. And also we use the recently introduced tandem detection cost function, which takes into account both the ASV system error and the countermeasure error into consideration. So let me talk about some results. So this is the quantitative results. And here we show the performance comparison of various generative models that we investigated. So the GM and different VA models. And we show the ER and TDCF. So lower the better. And as you can see, so what we found is when we used VA, two different VA models to model bona fide and spoof data, we found that was performance, and we found the model to perform well when we trained a single model, but condition on the class labels. So that setting showed good performance overall when we compare, and also we also augmented this experiment by conditioning more than class labels. So wherein we condition the models by using different past phrases of the corpus. So that also provided some improvement, though I didn't put those results here, I guess, because of the time. And yes, so the other result that I wanted to show you is regarding the second approach that we considered, where we used the VA as a feature extractor. But here, unlike in other approaches where people, where it's common to use the latent space as a feature representation, we didn't use this latent space, rather we used the residual features as a new feature representation. And on the backend, we trained the same CNN model, but we just vary the features, okay? So we see using VA residual features on the eval, which is the evaluation set. So this seemed to give encouraging results. And on the ER also, we see comparable performance, so which sort of motivates for us to investigate this further. And yeah, speaking of take-home message from this study we did, so one of the key challenges that we found was making the latent space retain discriminative information while also aiming to get a reasonable reconstruction. So this was one of the key challenges when we trained two separate VA models. And on top of that, later on when we condition these models using class labels, which that seemed to help retain discriminative information. And also auxiliary classifier didn't help much. So one reason could be that adding auxiliary classifier increased a lot of learnable parameters. And in case of 2017 dataset, the training data is quite less. And also we didn't optimize much on the parameters were not optimized. So yes, and speaking of future work, so we want to extend this preliminary study further in a frame level setting, and also we aim to investigate this work in a one class modeling approach, where we want to model only the genuine speech distribution and try to perform this class discrimination. So that's the current work on this. So that's all from my side. Thank you.